we are very happy to have for our third talk of the workshop, Emily Gunawan, who's a professor at the University of Massachusetts at Lowell, and she'll be telling us about pattern avoiding c-Birkhoff polytopes. So please.
Thank you very much for the introduction, and thank you to the organizers for having me. I'm very happy to tell you about a joint project with Esther Banyan, Sunita Chapuri, and Jianping Pan. So first, let me just summarize our main result. So what we did is, for each Coxeter element, we define a polytope, which is a subpolytope of the Birkhoff polytope, and there is some pattern of avoiding situation in this context. And then we prove that this polytope is in fact equivalent to an order polytope, and the poset for that order polytope comes from the C-sorting worth of the longest permutation. And because a lot of things are known about the order polytopes, we are able to compute the volume of our polytopes. So the normalized volume of our polytope is going to be the number of linear extensions of our poset H. And then this has connections to some other areas of mathematics. What was that? Oh, thank you. Thank you. So the number of linear extensions of the poset is the same as counting the number of longest chains in what's called the C-Cambrian lattice. So the C-Cambrian lattice has connection to cluster algebras. So the Hasse diagram of the C-Cambrian lattice is an oriented exchange graph of the cluster algebra with an initial quiver that can be described using C, which I'll explain in a little bit. And the C-Cambrian lattice can be like a special case of the C-Cambrian lattice is the Tamari lattice, which is the partial order on ways to use parentheses. So this is the case where your Coxeter element is of this form. And so this volume, if you look it up on OEIS, this is this entry for OEIS. And this also has connection to the representation theory of finite dimensional algebras. Our poset H can also be defined to be the Alexander-Rydzen quiver of graph cube, if you're familiar with that. All right. Okay, so our setup is that we have as our Coxeter group the symmetric group. On n+1 objects. And so this is generated by n simple transpositions, where each sk, in cycle notation, this is the permutation which swaps k and k+1. So our running example will be in A4. So this is generated by S1, which swaps 1 and 2, and then S2, which swaps 2 and 3, S3 and S4. And C will be our Coxeter element. So a Coxeter element of a Coxeter group, this is the product of all SK, so all n simple transpositions in any order. So for example, I can take my C here to be S1, S4, S2, S3. And I read my product from right to left, like reading function composition. So here, it's possible to check that in cycle notation, I get this permutation. And choosing a Coxeter element is equivalent to choosing an orientation of a type AN Dinkin diagram, which is the path graph with n vertices. So this is the Dinkin diagram of type AN. So there is a one-to-one correspondence between the Coxeter elements and Q, an orientation of this path graph. And the rule is as follows. So you would choose this orientation. So K plus 1 is pointing to K. If you see that in the Coxeter element, that SK is left of SK plus 1. So basically in the correct order, like K is earlier than K plus 1. And otherwise, you would point your arrow so that K goes to K plus 1. Yeah, so in this example, so because here, 1 is to the left of 2, I would point my arrow from S2 to S1. And then also S2 is to the left of S3, so I would point my arrow from S3 to S2. But 3 and 4 are out of order, so I would point my arrow from S3 to S4. And so I'm interested in what's called the heap of a permutation.
So it's always a path, like you always path and then you read.
Wait, sorry, can you repeat the question?
Q is always.
Yes, so Q is always going to be an orientation of this path graph.
But what if there are more instances for X1s?
Yeah, so yes, so that's a good question. So for if I have a Coxeter element, I'm just gonna have one copy. But in general, we can have multiple copies, so we'll have a more complicated picture. But in this special case, the heap of C is going to be this quiver. So this Q is quiver of C. But I just think of this as a Hasse diagram. That's labeled by the SK. So basically, I just take this quiver and just remove the orientation. Right, so now, but this is, I can think of it as the Hasse diagram of a poset. So this is called the heap of C. And then what is special about the heap in this case is that all reduced words of C are going to be linear extensions of this poset. So for example, this is one linear extension. So I do S1, S4, S2, S3. Or I could also do S1, S2, S4, S3. So that's a possible linear extension. I could also do S4, S1, S2, S3. And another thing that I want to mention is, so in general, to write my Coxeter element in cycle notation, what I can do is, I can write down the number 1 here, and then n plus 1 here. And then whenever I have an arrow like this, I would write down k plus 1 to the right. And if the number is below the arrow, I'm going to draw an underline. And if the number is above the arrow, I will draw an overline. So for example, I would do 2 underline, 3 underline, and then 4 overline. So I will refer to the underline numbers as just lower bar numbers, and the overline numbers as upper bar numbers. So what will happen here is I can just put all of the lower bar numbers. Let's call it D for put down. And I would do this in increasing order. And then over here, I would write down all of the upper bar numbers. Call it U for upper. And I do it in decreasing order. So in our example, there's only 1 upper bar numbers, and there are 2 lower bar numbers. So it fits this pattern.
Plus 1, which is in the middle. Just get in the middle of
Yeah, so in this example, this 5 is the n plus 1. And then in general, I can make a heap for any reduced word. It doesn't have to be the reduced word of a Coxeter element. So which I'm not going to explain, but I'll just say some properties of this heap. So if H is the heap of a reduced word of some Coxeter element of a Coxeter group, or in our case, we'll just work with permutation. So say this is my reduced word. Then just like in the previous situation, this reduced word is going to be a linear extension of H. And if you take all linear extensions of H, you get, so you don't necessarily get all of the reduced words, but you get the set of reduced words in the commutation class of A1 through AL. So this is all of the words that you would get by starting from the original reduced word, and then you take a sequence of what's called commutation moves. So that means if you have Si and Sj adjacent, you can swap the order. And you can do that whenever the difference between I and j is 2 or bigger. Okay, and then for our setup, I will now define the C sorting word. So this is a definition given by Nathan Reading. So a C sorting word of a permutation. This is going to be a reduced word of the permutation, and it is the lexicographically first as a sequence of positions in this infinite word where I write C just infinitely many times. Call this C infinity. So this is the lexicographically first subword of C infinity that is a reduced word for W. And we will denote this by sort C of W. And I'm most interested in the C sorting word of the longest permutation. So W naught will be the longest permutation. And in one line notation, that is going to be the reverse of the identity permutation. So you start with n plus 1, n, 3, 2, 1. So this is in one line notation. So in our example, in A4 or S5, our W naught is 5, 4, 3, 2, 1 in one line notation. And then the Coxeter length of the longest permutation. So this is the length of any reduced word of the permutation is called Coxeter length, and it is n plus 1 choose 2. So in our example, it is 5 choose 2, which is 10. And even though I am interested in the C sorting word of W naught, for our polytope, we're actually more interested in the heap of this C sorting word. So instead of writing down the C sorting word, I'm just going to tell you how to construct the heap. Yes, so let's do it for this running example. So actually, let me just write down the C So my C was. So for short, instead of writing the S, I'm just gonna write 1, 4, 2, 3. This really means S1, S4, S2, S3. So then my C infinity, 1, 4, 2, 3, 1, 4, 2, 3, 1, 4, 2, 3, and so on. So in this example, I can take 1, 4, 2, 3, and then 1, 4, 2, 3, and 1, 2. So this is, oh wait, it's hard to see because the circles are big. 1, 2. Okay, so if I take S1, S4, S2, S3, and then repeat, and then S1, S2. This is the C sorting word of my longest permutation. Yes, okay. So here's how you make the heap of the C sorting word in general. So this is also like it's well known how to do this, or like it's written in the literature. So the first thing that I will do is I will refer to a diagonal as a line with slope -1. So I have this long diagonal where I basically write down all of the simple reflections. And then the next step is for each lower bar number, I write down another diagonal. So if my lower bar number is D, then I write down this D-1 vertices starting from S1. So because my lower bar number is 3, I write down S1, S2. And then my other lower bar number is 2, so I write down S1. And then the next thing I do is above the long diagonal for each, this should be upper bar. So for each upper bar number, I write down a diagonal that ends at Sn. And also it's going to be U-1 vertices. So in this example, because I have U is 4, so U-1 is 3, I write down this diagonal with 3 vertices. So the label here are important, like I want to know, but basically here I have 1, 2, 3, 4. So it's always going to be in this order. And then for convenience, so I want to give names to my elements of the poset. So the elements are just 1 through L, where L is the length of W0. And I'm going to follow this diagonal reading word, where basically I read in this way, or I follow this order, 1 through 10. Question?
So earlier when Nicole asked you for an example of the C sorting word, and then you pick them out, and then I sat here like checking that they actually multiply the bottom element because it wasn't obvious to me. but like I can see it in that heap, right? Is that the point? Like that's how you understood what the heap was going to be. The like I can see the 1, 2, 3, 4 and the 1, 2, 3, 4 and the 1, 2 in that picture, and that was how you were able to pick that out.
Yes, so the question was like, was I able to quickly see what the C sorting word should be from the heap? Yeah, so this is one way where you can quickly compute it by hand. Question?
How you get that heap from, what's the starting, the C starting word before or?
Oh, so yeah, so the definition is like you would start from this. So this is, so this is sort CW naught. So the definition is like you would start from this and then you build this heap, which I haven't defined. But another way is to just look at the upper and lower bar numbers and then quickly make that heap. Okay, and then for people who are interested in finite dimensional algebras, here was the connection that I said earlier. So if I take my heap H and I rotate it by 90-degree clockwise, this gives us what's called the combinatorial AR quiver. And this name is because the graph that you get is isomorphic to the Auslander-Ruyten quiver of that quiver coming from C that I defined earlier. So for example, here is what we have. So I can take my heap and rotate it by 90. Let's see. Oh, this word, thank you. Okay. Okay, so now you see that it's this graph. Yes. Yeah, but this is the actual Auslander-Ruyten quiver of that quiver. Okay, so now I want to talk about order polytopes. So given a finite poset, the order polytope of that poset, it's going to be the set of vectors in the cardinality of H dimensional space, where the entries of that vector is between 1 and 0. And then it satisfies this poset relation. So you would have the entry at I is smaller than the entry at J whenever I is smaller than J in the poset H. And so this is a very nice polytope. The dimension is exactly the cardinality of H, so it's full dimensional. And then instead of defining it this way, what you can do is just take the convex hull of the vertices and the vertices of an order polytope is equal to the set of indicator vectors of I, where I is an order ideal or downset. of H. Yeah, so then you can just take the order polytope to be the convex hull of the indicator vectors of the order ideals of H. So for example, here I have my poset H, and I take these to be my order ideal I. So my indicator vector is just choosing one whenever these are in the order ideal, and then 0 everywhere else. And then another thing that's nice is the volume is easier to compute than a typical polytope. So the normalized volume is equal to taking the dimension of a polytope and then taking the factorial of that and multiply that with the Euclidean volume. And this is an integer, and it is the number of linear extensions of H. Okay. Yeah, so in this example, the dimension of the order polytope coming from this H is 10, because there are 10 elements in a poset. And then we also compute the volume by counting the number of linear extensions. So by computer, we check there are 41 linear extensions. Which one? Oh, was I, oh, because it was, yes. Full screen. Okay, so that's the order polytope. So our polytope, we said is integrally equivalent to this polytope. So now I'm going to define c-singletons. So instead of actually defining it, I'm going to write down some characterizations. So the following are equivalent. So a permutation is called c-singleton. So this was defined by Holweg and Lange and Thomas soon after the C-sorting word was defined. But this, so if W is a C-singleton, if and only if W corresponds to an order ideal of H, where H was the poset I defined earlier, the heap. So that means really is that W has a reduced word, which is a linear extension of I. So for example, if this is my I, actually, let me copy the, didn't work. Oh, sorry, I should do this one. Sorry for scrolling. Okay, so if I have 1, 2, 4, 5, 8, because so I would do 1, 1, 2, 4, 5, 8, and I would just write down the labels that I see here. So the permutation corresponding to I here would be S1, S2, S4, S3, S4, like this. And another way to check whether a permutation is a C-singleton is that this permutation avoids 4 certain patterns. So this is true for all n, not just in our example. So I'll write down the patterns. It's a more general permutation pattern avoidance than the classical one. And just a remark that if our C is of this form, then the 4 patterns collapse to just 2 patterns. So W is a C-singleton. If and only if it avoids the pattern 312 and 132 in a classical way, the usual way. And this is the one that corresponds to the Tamari lattice. But the definition that I will use this, like thinking of the C-singletons as order ideals. And do I go for 15 more minutes? Is that right? Okay, so now I can define our polytope. So given a Coxeter element, we define BERC to be the convex hull of the permutation matrices. Let's call it MW of all of the C-singletons W. And just to write down the definition. So my permutation matrix would be, so this is an n plus 1 by n plus 1 matrix. So this is gonna have entry, let's see. So the row I and column J will have entry 1 if the permutation sends I to J, and 0 otherwise. And I think I have an example here. So yes, so if this is my order ideal, so this would give me a C-singleton. And this corresponds to doing the reduced word S1, S2, S1. And in 2-line notation, I get this permutation. And this would be my permutation matrix. And because there are 25 possible entries, this is a vector in R25. And this is a subpolytope of the Birkhoff polytope because, let me just write that. So one way to think about the Birkhoff polytope is to think of it as the convex hull of all permutation matrices. And the vertices of the Birkhoff polytope are all of the permutation matrices. And in our case, our vertices are exactly all of the permutation matrices coming from C-singletons. And now I just want to remark that so like you see in our example, our BirkC, our polytope, it lives in this ambient space of R25. So in general, it is n+1 squared. But it is actually the dimension is smaller. It has dimension n+1 choose 2. So that's the number of elements in the poset. So in our example, it was 10. So I'm just gonna give you the relations that let us go from dimension 25 to dimension 10 in our example. So here for the Birkhoff polytope itself, but there is a condition that requires each row and column to sum up to 1. So for example, if you know what these are, then you know what this entry must be. So then we have 9 positions that is determined by all of the other positions. So here I can take -9. And then the pattern avoidance conditions I said earlier that tell us that some of the entries must be 0 because certain positions are not allowed. So in this example, so this is 2 and 3. So the fact that 2 and 3 are lower bar and 4 is upper bar tell me that I must have these 0 entries. So this gives me -4. And then the pattern avoidance conditions also tell me that there is some other relation. So here it must be that all of these entries sum to 1. So that gives me another -1. And also these entries must sum up to 1. So again, -1. So if I add all of them up, I get -15. So I was able to go from dimension 25 to dimension 10 in this way. Okay, so the main result was that our Birkhoff or our c-Birkhoff polytope is integrally equivalent to the order polytope of H. So that allows us to know many nice properties that we know from the order polytope. So let's see. So I'll just kind of give an idea of our proof. So what we do is we have this projection pi c, where in this example we go from the 5 by 5 matrices in MAAGC. And then we just choose 10 entries. And this gets us to R10. And the things I have written here by a number are like the things that I am choosing. So yeah, so basically I'm starting to read from column 2 and column 3 because of the lower bars 2 and 3. So the first thing I'm choosing is 10. And then I'm also choosing 9 and 8. And then after that, I kind of jump to the last column. So this is the n+1 column, and then just read that column. So 7, 6, 5, 4. And then after that, there are some extra rules that tell me what to do in the situation for the upper bar numbers. And this map sends integral points to integral points. And then we also prove that there is a unique n+1 choose 2 by n+1 choose 2 lower triangular matrix with ones on the main diagonal. So this tells us that the determinant of U is 1. And when we compose the two things, pi c and U, and then this composition sends the matrix to the indicator vector of the order ideal I of H that corresponds to W. Okay, so yeah, so that's the idea of the proof. And now in conclusion, I want to go back to the beginning, so to talk about the inspiration for this project. So I mentioned this OAIS sequence. So if you look on the page, you will see that it counts the longest chains in a Tamari lattice. And then it also counts the normalized volume of this polytope, which is the convex hull of permutation matrices, avoiding 312 and 132. And there's a comment that basically says that it counts the linear extensions of this poset H, and this corresponds to the outside right quiver of the quiver that's just all pointing in the same direction. And yeah, and this is basically saying this is counting the volume of this same order polytope. And so so this project was inspired because of this OAS entry. So what we have is basically a generalization of this, where for this OAS entry, this corresponds to where C is of this form. But now we're able to do this for all Coxeter elements. All right, and then some natural questions is if instead of taking the heap of the C sorting word of W naught, I could take the heap of any reduced word. So then can I play the same game where like can I get this correspondence between the world of order polytopes and just some convex hull of permutation matrices. So it is often the case, but it's not true in general. So we have just two counter examples in A4. So this is an example of a reduced word of W naught actually, and this is the corresponding heap. And in this case, we don't get the same polytopes. But but it's interesting to ask when it happens. And then another thing is to generalize this to other Coxeter groups. And the answer is no in general, but it seems to be true in some situations. And I will stop here. Thank you very much for your attention.
Question.
No. Go ahead. Or-
I think for the next one, so so this connection with the linear extensions and the reduced words, is there also a connection with the like order, like maps or order presented maps, so you want to already make all distinct elements and some subwords and yeah, okay.
Wait, so instead of linear extension, you just want to take an order preserving map?
Yes. Yeah, we can read it. Okay, but then I have two other questions for the Combinatorics, you get the staircase. Are there other nice cases where you get some nice tableau?
So maybe, so in general, it's like in this example. So I'm not sure if you consider, is this one, is this nice enough? So yeah, so in general, it's always going to be this type of shape of like in type A, there are boxes like this. And maybe then the other extreme. So if this is the linear case, the other extreme is the bipartite case, where you have this shape. And here the linear extensions, the number is as big as possible, conjecturally. Because the Tamari case is when the volume is as small as possible. Yes.
Okay, the Birkhoff polytopes are lower dimension factors for the Birkhoff polytope. If you take the union of all Birkhoffs, that's some sort of structure inside the Birkhoff polytope. Does it relate to the Birkhoff polytope in a nice way?
That's a good question. I'm not sure.
Yeah.